5-1, polynomial functions. So our objective for this section is to, number one, to classify polynomials, and then to graph polynomial functions and describe the end behavior. So we're going to shy a little bit away from the graphing, and we'll stick more with describing how a polynomial works based on the equation. And our essential understanding is that a polynomial function has distinguishing behaviors, things that happen that we can tell just by looking at an equation. We can look at its algebraic form and know something about its graph. You can look at its graph and know something about its algebraic form. It goes either way. Okay. So first, some vocabulary. All right. A monomial. Okay. Should all know what this is. Mono, right, from Greek means one. So monomial is a real number, a variable, or a product of a real number and one or more variables with whole number exponents. Something that looks like that. That is a monomial because we are multiplying a real number and a variable together. Okay. The degree of a monomial in one variable, okay, we could talk about degree in more than one variable, but we're going to stick with one variable for this. So the degree of a monomial in one variable is the exponent of that variable. So this particular monomial would have a degree of 3. Okay. Next, polynomial is a monomial or a sum of monomials. So 2x to the third power right here could be a polynomial, right? But we can further classify it as a monomial. A polynomial can also be a sum of monomials, something like that. Okay, that is a polynomial because it has a bunch of monomials added together. It is not a monomial because it's not a product. It is a sum. Okay, so when we sum things together, we turn things from monomials from one term into something with this particular one has 4 terms. Okay, so now the degree of a polynomial in one variable, again, okay, so the degree of the polynomial in one variable is the greatest degree among its monomial terms. So the degree of this polynomial is 3. We don't have to worry about these other exponents, okay? All we have to do is look at the largest exponent, the term with the biggest exponent. A polynomial with a variable x defines a polynomial function. Okay, that's just notation. If I wanted to, I can turn this into a polynomial function with function notation using my f of x equals the function in terms of x. The degree of this function is the same as the degree of the polynomial. It is a degree 3. So, standard form of a polynomial function. Okay, my standard form arranges the terms by degree in descending numerical order. So what we're going to do is we're going to take some sort of polynomial. If we see a polynomial, we're going to take it, put the largest exponent first, and then list them going from biggest exponents down to the smallest exponents down to the constant term. The correct way to write this in the very general form looks like this expression right there. Looks confusing, but don't let it confuse you. You're going to see this a lot, right? It's just the standard form of a polynomial function. Those are subscripts. So a is going to be the coefficient, n is the subscript. So this is the a, this term right here is a sub n times x to the nth power. So that just means the coefficient in front of the term with the nth exponent. That means this term right here means the coefficient in front of the term with the n minus 1 exponent, all the way down to the linear term, the x to the first power. And then my last term is a sub 0 because there is no variable in my last and my constant term. Okay? So don't get confused too much with the notation of a polynomial in standard form. All it means is we start with the largest exponent and we get smaller each time until we get down to nothing. And it's just a way to rewrite and classify these polynomials. So when we look at these, we see that we can name each one of these terms based on the degree of their by the degree of that particular term. And we have special names for a bunch of these things. So we can classify a polynomial by its degree or by its number of terms. So polynomials degree 0 through 5 have specific names, just like it's in this table. So if something has a degree of 0, it's called a constant. If something has a degree of 1, it's called linear. Degree 2 is quadratic. Degree 3 is cubic. Degree 4 is quartic. And degree 5 is quintic. Now, as we go higher, we do have names for those different degrees, but we're not going to worry about them in this class. So for degree 6 and up, we're just going to say 6th degree, or you know, as we get higher and higher, 7th degree, 8th degree, 9th degree, whatever. Okay, so we are going to use the names of the polynomials from 1 to 5. We're going to use their special names, but as we get higher than 5, we're just going to use the generic names. Now, over to number of terms right here. The number of terms also have special names. So if it is 1 term, it's called a monomial. If it is 2 terms, it's called a binomial. If it is 3 terms, it's called a trinomial. And then after that, we're going to start using generic terms again. So for instance, 5 would be a polynomial, more room, would be a polynomial of 5 terms. Okay. So as we go and as we go down, we're going to use the same sort of naming standard. So when we're looking at these polynomials, these examples right here, we're going to name them with both by degree and by number of terms. So we're going to use one name from this column and one name from this column in order to name this polynomial. So for instance, 5 would be a constant monomial. X plus 4 would be a linear binomial. 4x squared would be a quadratic, because it's second degree, monomial, 1 term. This one right here would be a cubic trinomial, 1, 2, 3 terms, and it's to the 3rd power, cubic trinomial. 2x to the 4th plus 5x squared, look for the biggest exponent, that's to the 4th, so that is a quartic binomial. And then the last one, a quintic polynomial of 4 terms. So, write each polynomial in standard form. What is this classification of each polynomial by degree, by number of terms? So the first thing we're going to have to do when we write these in standard form is make sure that any like terms we add together, and we put it in descending order of degree. So the biggest degree goes first, and then we go down to the last one. So for part A right here, pretty simple. My largest degree is right there. So we write this as 9x squared plus 3x plus 5. Okay. And now we name it by degree and by number of terms. It's a degree 2, and it has 1, 2, 3 terms. So degree 2, if we look back at our table, degree 2 is a quadratic. The number of terms is a trinomial. So this particular polynomial would be a quadratic trinomial. Okay? Weird eye. Okay? Down here for B, rearrange it with the biggest exponent first. The biggest one is x to the 4th. Okay? There is no x to the 3rd. That's okay. Then I have negative 6x squared and 10x squared. Those are like terms. We can put them together. So that turns into 4x squared. Now, of course, when you're adding like terms, don't forget that the exponents stay the same. Only thing that changes is the coefficient. Plus my 4x that was out front right there, minus 12. Now I can look at this polynomial and decide what is my degree. It's a degree 4. How many terms is it? 1, 2, 3, 4. So this is a quartic polynomial of 4 terms. Good. Next, the degree of a polynomial function affects its shape of its graph and determines the maximum number of turning points, or places where the graph changes direction. It also affects the end behavior, or the directions of the graph at the far left and the far right. Think about this. If we have something that is the first degree, that would be a line. That would be something that looks like this. That's the first degree. That would be a line. Okay? That means one end is going down, one end is going up. Or perhaps the other way. We could turn it to be like this. But then you should realize that in order to have a line like that, I would have to have a negative slope. That means there would be a negative in front of x. That means one end goes up, one end goes down. If I think about what the graph of this parent function looks like, x squared, it looks like a parabola. It looks something like that. That means both ends are going the same direction. They're both going up. If I had a parabola that looks like this, I should remember that that means that a has to be negative. That number in front of x squared has to be negative. And now both ends are going down. So based on those two simple ones, we can sort of make a table. We can make a table that shows me the directions that the ends are going. And so the table below shows you examples of polynomial functions and the 4 types of end behavior. The table also shows intervals where the functions are increasing and decreasing. A function is increasing when the y values increase. So we'll talk about increasing and decreasing in a minute. But first, let's look at the table for end behavior. Okay? So we can determine the end behavior of a polynomial function of degree n. So n is the exponent from the leading term. So whatever is first. So leading term means this term, the first term, when it is in standard form. This term, the first term, when it is in standard form. It wasn't the first term when I started, but it's the first term when I put it into standard form. Okay, that's what we mean by leading term. So the leading term of the standard form. Okay, so we look at the number in front and we look at the exponent. The number in front, we see if it is positive or negative. The exponent, we see if it is even or odd. And then, depending what they are, we can see that the function either has both ends going up, both ends going down, if n is even and a is positive or negative, or one end going down and up and the other up and down. And these go from left to right. So this means left end going up, right end going down. Left end going down, right end going down. Left end down, right up. Left end up, right end down. Okay. So it depends. It depends on whether a is positive or negative and n is even or odd. And this chart shows the graph from left to right. So if I look at a few types of polynomial functions, I can see, number one, that this is a positive number and this is an even exponent. So that means both ends go up and up. Okay? This particular graph has 1, 2, 3 turning points. Okay? And then we can see by the graph that the graph is decreasing until it turns, then increasing, decreasing, increasing. And that's just a matter of looking at the graph. For this one on the right, we can see that the leading coefficient, the number in front of x squared, is negative, because it's a negative 1, and my exponent is even. Negative and even tell me that both ends go down, which they do. And this particular graph has 1 turning point, and it is increasing till it turns around and then decreasing. Okay, and that should be a pretty simple parabola for everybody to take a look at. Okay. Two more with odd exponents, where my A is positive, so that's positive and odd. So my end behavior is down and up, which means that it's down as I go to the left and up as I go to the right. And for now, we'll stick with just describing the end behavior like that. As you get more advanced and as you get into pre-calc, then you'll have to describe the end behavior using something called limits. But for now, we're just going to describe what the graph is doing. Here, it's going down to the left and up to the right. For the second one over on the right, we can see that the leading coefficient is negative and the exponent is odd. So that means my end behavior is up and down, which means up as it goes to the left, down as it goes to the right. And this particular graph back on the left has no turning points. This one has 2. So we can sort of make a assumption based on these 4 pictures right here. This was something to the 4th power. It had 3 turning points. This one was something to the 2nd power. It had 1 turning point. This one was to the 3rd power. It had none. And this same one this different one over here is also to the 3rd power, and it had 2 turning points. So that leads us to something that we can say about a graph and the number of turning points that it has. So in general, the graph of a polynomial function of degree n, just something bigger than 1, something more than a line, has at most n minus 1 turning points. At most, not exactly, at most. Because as we saw in this picture right here, this is to the 3rd power. It had none. This is to the 3rd power. It had 2. So you can't necessarily tell exactly how many turning points a graph will have just by looking at the equation, but you can tell its maximum number of turning points. And you know that the graph of a polynomial function of odd degree has an even number of turning points, and the graph of a polynomial function of even degree has an odd number of turning points. So, describing the end behavior of a polynomial function, consider the leading term of each polynomial function. What is the end behavior of the graph? Okay, then if you want to, you can check it with a graphing calculator or to graph it on your Desmos app. But for now, we're just going to look at this, and we're going to see that this is my lead term is positive, and my exponent is odd. So with a positive and odd function, I should know that my graph goes down and up, down to the left, up to the right. And I can tell that just by looking at this chart right here. Positive and odd, down and up. And I can also tell that this particular function, okay, that function right there, will have at most 2 turning points, 1 less than its biggest exponent. Now, does it have 2 turning points? Probably, but we can't know for sure until we actually graph it. B, looking at my lead term. First things first, make sure, take a look at the whole function. Is it in standard form? If it's not in standard form, make it into standard form. Okay. So I'm looking at my lead term. A is negative, N is even. So with negative, even polynomials, they go down and down. Okay, both ends go down. And then if I want to go back to the beginning and name this polynomial in part A, it would be a cubic binomial. If I want to name the polynomial in part B, that would be a quartic polynomial of 4 terms. So, suppose you're given a set of polynomial function outputs. You're given a table with just data. You know that their inputs are an ordered set of x values. That's important. Ordered set, got to be in order, in which consecutive x values differ by a constant. So you're either going to go up by 2 or up by 1. Most of the time we're going to go up by 1. By analyzing the differences of consecutive y values, it's possible to determine the least degree polynomial function that could generate the data. If the first differences are constant, the function is linear. If the second differences, but not the first, are constant, the function is quadratic. If the third differences, but not the second, are constant, the function is cubic, and so on. So what does that mean? That means that we can take this polynomial function and we can take this data, and as long as everything's in order, we can figure out what degree the polynomial is that made that data, like a problem just like this. Okay, so using the differences to determine degree. What's the degree of the polynomial function that generates the data at the table, which is below, not at the right, but okay. So what we're going to do first is double check that all my x values, all my inputs are in order and they're constant, which they are. They all differ by 1. Okay, so what we do next is we find the differences. We find the differences between the y values. For instance, we find the difference between -7 minus -1. We want to subtract this one from that one, and we get -6. And then we do the same thing for all the terms. So doing that gives me a 4 here. I get +4, -3 minus -7, and 8, 6, -2, and -16. Now, those are my first differences. Okay? So my first differences are not the same. If they were the same, this would be a line, but they're not the same. So what do I do next? I have to find the second differences. So we try to find the second differences. Let's put this up here. Second differences. Okay? So I do the same thing again. I take 4 minus -6, 8 minus 4, 6 minus 8, -2 minus 6, and 16 minus -2. And I figure out my differences. 4 minus -6 gives me a 10, a 4, a -2, a -8, and a -14. So looking at my second differences, I see that they are still not the same. If they were the same, this would be a quadratic. This would be x squared. But they're not the same. I keep going. And we see go 4 minus 10 gives me -6. And look, all my differences are the same. So that means this is a third degree polynomial. And I can arrive at that by taking the differences. Okay? We don't start counting with the output values. We start counting with the first difference, the second difference, the third difference. This is a third degree polynomial function. And that is 5-1.